Good afternoon or good evening, everyone. I hope that you took a proper rest from yesterday. Today we are going to continue and we are going to tackle practical hardware design considerations for embedded platform and machine learning part 2. But before that, before we continue, I have a few questions for you. So the first question is, can you tell me like 2 major points you took away from yesterday part in general? It can be whatever. Do you hear me properly or? Okay. The question. Okay, so if someone can tell me, for example, 2 major points which were taken yesterday from yesterday presentation, or 1, doesn't matter. It is enough already. Okay, well, then I will just shortly wrap up the what we did yesterday. So yesterday we started with the hardware part. This is a shorter part, but nevertheless, we did some small overview of the common architectures used in the edge embedded devices for ML. We also tackled the hardware design of these platforms in a methodological way. And we also started some practical design considerations. The last thing we did yesterday, it was actually the architecture of the system requirements I presented at the very beginning of the last presentation. And today we are going to continue. So what I promised to you is that I will show you actually the architecture, what we implemented or how we did it, and we will briefly discuss that. This practical consideration part is meant just to walk you through the all stages of the, let's say, design in a practical sense, so that you understand things through the design from concept, from the requirements until to the production of the PCB and assembly of the PCB. So to go through all these steps, what we presented in theoretical way as a methodological part through the design. Of course, this is very shortened version, but nevertheless, I just want to give you an impression how it looks like. Yesterday, when we had these discussions about architectures, that's how actually it looks like in industry. So you will have a series of meetings. Different people will be there. They will be just discussing. Sometimes these meetings are fruitful, sometimes not. But that's all part of that professional story, I would say. So I will then directly jump to the architecture. Yes, so just to come there. Okay, so this is the architecture. Don't get confused. This is actually very simple, and I will explain you first of all how to read these kind of diagrams, because you see different colors, you see some notes here. So the very first thing you should do is you should just look for example, notes. You see that this color pink color or something similar, it actually denotes the power domain. This power domain. So wherever you see this color like this, you will know that this is power domain. Then you have a yellow, and this is digital domain. So you can see that we have a here digital domain. Then you have blue color, which represents the analog domain of the device. Then you have gray color. It is it denotes the internal connectors. Internal connectors. And you have a green one, which represents the external connectors. What does it mean, internal and external connectors? Well, some devices have connectors which normally user cannot access them. They are just used for some debugging purposes or troubleshooting purposes, and they can be accessed only by, let's say, authorized personnel. So it means that they will open the device, and then they will be able to connect to some debug ports, UART or USBs, and so on. But normally they are not accessible for the user. And of course, external connectors, user can access them normally. Okay, so if we go now into the this block diagram, we can see, first of all, interfaces. We have a micro USB connector. Then we have a connector for altimeter. Then for GPS or GNSS module, whatever it is. And we have it for short range radio. If you remember, this radio was on 433. This can be whatever, GPS, GLONASS, Beidou, whatever constellation. Then we have, of course, for altimeter connector. Then we have connector for the sensor here. And we have connector for the high voltage power supply for the sensor. So we have a lot of connectors which connects this device to external components. And that is, I would say, a tricky part to design if you take into account the EMC requirements. Then here you have power supply domain. Mike, just one question. Can you properly see the letters, or should I maybe enlarge this by the segments or not? So can you see, for example, what is written here? Barely. Okay, no problem. Let's see now. Is it now better?
Yeah, much better.
No problem. So this is a PMIC, which actually arbitrates between power supply from a micro USB connector and from a lithium battery. Then when this arbitration is done, we will provide this to the buck converter, which will just put or do the step down of the voltage from 5.5 to 3.3 volts. And you can see here that this goes to microcontroller and eMMC. What we used here as a key components, we didn't use a processor. As we said yesterday, we use an FPGA. This is Artix. And we use one microcontroller here, which doesn't have any kind of accelerators, nothing. It's a just standard microcontroller from STM. Then we also use the memory where we store the data, but we also here store configuration for the FPGA. And what has been done here is that we actually configure the FPGA using a microcontroller. As you can see, we don't have any memory to store configuration for FPGA, which is directly connected to FPGA. Rather, we share this memory for data storage, and we share it for configuration storage. we have a clock generator. This clock generator provides actually clock for two different components. It provides it for FPGA, one output, and the other goes to ADC. What is very important here is this is configurable clock generator. See that it is connected via I2C to the microcontroller. So microcontroller can change this frequency. This is just the analog part. So we have this transimpedance amplifier, ADC driver, ADC, and that's the whole chain. I have a question. We have here LDOs, and they are in blue color. They are part of the analog front end, but they are actually power supplies. What do you think? Why we used LDOs here to supply ADCs and this driver?
They have less noise than a switching converter.
Yes, they have less noise, and this is the usual. This is the very ubiquitous approach. So we have here actually a switching mode power supplies, which are noisy. And if we bring this power supply to this analog front end, we are going to contaminate it with the noise, of course. What we are going to do, we are going to increase the noise floor, and we will reduce the dynamic range of this chain, which we don't want to do, of course. Okay. I have a question. What do you think? Why we provided a separate power supply just for microcontroller and eMMC? So just one power supply dedicated for microcontroller. Let's just say microcontroller. Forget eMMC. It's not important for this question. We want to make optimized solution in terms of power consumption. I can help you maybe with the answer.
Because you want to sequence the power up, maybe you want to first power up the microcontroller and then the FPGA.
Yes, exactly. So, well, what was our approach here is following. When you apply a battery or you apply a power supply over micro USB, you will just turn on or bring power supply to the microcontroller, and that's all. The rest of the board is literally dead. So nothing is powered up. You don't have a power supply. You don't have anything. So in order to power on all other devices on the PCB, you need actually to write code in microcontroller which will handle that in a proper manner. But if it's like I said, why did we use PMIC for FPGA then? Because we do not control the sequence for FPGA with microcontroller. It is actually controlled with a PMIC. But on the other side, as you can see, we have a connection I2C via I2C bus between FPGA, PMIC, and microcontroller. What is done at this stage? Well, you can program the output voltages here in some small range. So before you turn on power rails here, A microcontroller will actually configure, it will write into a register of this PMIC some values, and it will set the output voltages. It will also write values for delays and for the right sequence. And when all that is configured in this PMIC, we will just enable the output voltages, and we will power supply the FPGA. The same thing comes with this high voltage regulator. We have a SPI bus that will be used to configure the output voltage, the value of the output voltage, and also to enable the voltage. Okay, so this is how we control these power supplies. And as you can see, for this buck converter, it's not controlled by anything. It simply gets the input voltage and simply gives the output voltage. So it means really when we plug in the battery or a micro USB connector, we will immediately get here the voltage, and nothing will stop that. Okay, I have a question. If this is done in this way, does it mean that we always need a microcontroller to control the PMIC, which is necessary when we use components like FPGAs, CPUs, GPUs, and so on? Does it mean that we always need to have some small microcontroller next to it that can control the power-up sequence? What would be your logical reasoning? So imagine, for example, then that the whole industry wants to decrease the bill of material, the BOM, the number of components, and now we are forced to have always a microcontroller when we have a PMIC. So what would be your logical reasoning? Is it really necessary, or how it can be resolved?
I think it depends on the complexity of what you want to control, especially in these situations. Maybe you always turn on the power system the same way, so you could do this with some logic stuff that you can make instead of using a whole and a big microcontroller, I guess.
Okay, so what is usually done is when some new component, for example, is on the market, like some new FPGA or some component which requires some special sequence, some of the manufacturers will always make a PMIC which has some default values, which are in the range that particular component can accept and can start up, actually. So usually you will have some PMIC which has default output values which can be immediately used out of the box. So what does it mean? It means that we would not need a microcontroller for that. But why we selected to have microcontroller here, it is due to different reasons. But when we needed to have it, then we just say, okay, let's then control also the PMIC with microcontroller, because it just gives us flexibility. We can turn on and turn off FPGA if we want, and we can, in that sense, preserve the power. But if we would use a system on chip, like or an FPGA which has also some hard cores on silicon, like zinc, we would not be able to do that. We would not have that kind of flexibility. For example, we want to turn off all the peripherals. We want to be in a mode of power consumption which is minimal. We cannot do that because once we turn off, we cannot turn on the system. But in this way, we can do that. Okay, and also we use microcontroller to communicate over USB. So you see here. There is a connection. And microcontroller is connected to FPGA with SPI, as you can see. And these are signals and interface to configure the FPGA by microcontroller. So what microcontroller does, microcontroller actually takes the configuration from this memory here and just configures the FPGA. There is, of course, a function or functions inside which do that. There is also a function which will receive the configuration through the USB from a host system, which is usually a desktop or notebook. Then it will store it here. And then each time you boot the system, it will just configure the FPGA. For this, of course, you need to have an application on a host system which will handshake and communicate with the microcontroller over USB. Okay, let's briefly tackle the clock generator. What do you think about the clock generator in terms of where it should be positioned? You properly said that we use LDOs for filtering the noise and providing a proper power supply, so very low noise power supply for analog content. But what about this? We need to put the clock generator to clock actually the ADC. And we know that clock generator produces a lot of interference. How do we tackle this problem? Where should we position the clock generator in order not to interfere with the sensitive analog content? My question is, should we put the clock generator closer to the ADC and have short interconnects between this component and this component? Or should we put it closer to FPGA and have longer interconnect between clock generator and ADC? What would be your approach here? What would be your selection?
I wouldn't like to have such a high frequency signal going around the board unnecessarily. So I think how is it?
So
way of like having the same distance, the shorter I can to both systems. So at least the longest connection is still short, and I'm like spreading signal across all the PCB, for example.
okay, yeah, that's a valid reasoning. I would say both of these. So yes, you don't want, for example, the first colleague who said, I don't want like long traces where we have a clock signals to go around the PCB. Yes, we don't want that. Of course, we don't want that. That's a right approach. The approach that we actually have very close to both, so to have more or less the same distances, it's also a valid approach. I would just, yeah, maybe suggest the third approach. So maybe you can put the clock generator a bit further from this part, and let's say use a longer interconnect. But then I would apply certain technique, like for example, via stitching around the track to protect the rest of the PCB from this, let's say, highly noise interconnect. You understand what I want to say? So maybe something like this. I will just share my screen in a whiteboard, actually. Just a second.
Like to shield the paths of the wires. Yeah.
So then I will not share. So yeah, to shield, you can use that. because if you put the component which is switching very fast, like oscillator, close to the let's say analog front end, it will simply radiate. It will contaminate the analog front end if you do not shield it. If you want to shield it, the component, it means additional cost. You need to actually buy a shield, and it has one additional step in production, in assembly. You need to put it there. But in this way, we are just using the resources of the PCB, which are basically have zero cost. If you add 20 more vias, it will not make a difference in price of the PCB. So that's what we would like to do. Okay.
Pathways of the clock generator to the devices in different ways as microchip lines or different waveguides into the PCB because it can concentrate the electrical field. The EMC can be managed.
If I understood, you said a different another PCB which would be stacked on this one, or no?
Into the same PCB, we have a lot of different kind of signals, and then an approach is supposed can be used is the clock generator waves or signals can be connected to the devices as FPGA microcontroller through microchip lines or different kind of waveguides into the PCB because we can concentrate the electrical field there and then put the control into the into the rest of the PCB.
I understand your point. So basically, you are saying this. Just a second. So you are saying this that we have, if this is, for example, let's say like this, PCB stack up. We have like a top layer, inner layer 1, inner layer 2, let's say inner layer 3. And then you want to say that, for example, if we have a component here, which is clock generator, I would just write oscillator, then this is a pin that we go for, and this is a ground layer, and this is a ground layer. And then we can go in this layer here, and using so-called strip line structure, and then coming here, the sample analog front end to the ADC, and coming to the pin, if I properly understood.
Into the inner stack PCB can be designed as microchip lamps or different waveguides in order to concentrate the field. And this is a good approach because different ME control phenomena into the PCB can be concentrated into different parts.
Yes, but okay. In this scenario here, for example, we would have a strip line structure which is confined between two ground layers. So the field will be confined here. That's true. But what happens what happens here with the transition of layers? This will be something which will generate common mode currents because we switch the layers, and the return path of this signal is not, let's say, so straightforward. If we do the following thing, if we just use top layer and tightly coupled a ground layer below, so this is inner one, and we use a microstrip structure. So this is oscillator, and this is ADC. So we use this connection here and use stitching vias. Stitching vias from top view, they would look like this. This is a top view of the PCB. So we have oscillator, we have ADC, and we have a strip line. So if we stitch vias here, and if we tightly couple this to the ground, we will confine the electromagnetic field. Basically, okay, we will have a leakage on these sides, but basically most will be actually confined here. So again, we will succeed in the intention not to interfere with the analog front end. But in order not to couple to the other signals which can be here, we should provide this stitching here.
Why do you prefer stitching vias instead of putting like two paths around it, like shielding literally with another path connected to ground?
Yeah. Good question. Good question. I will tell you. So when you do like this here, you have a very simple return path. So return path of your signal will be actually here beneath this one, and it will be, everything will be confined and very tight. So in this way, you will not produce common mode currents. But if you use this approach here, when you change the layers,
putting two paths one next to the other, instead of having multiple stitched vias, put one straight line at the right and left of that path that you want to shield from the rest of the PCB.
Okay, I understand your point. I will just tell you how it looks like in practice. You will see. So in practice, I'm now looking at the top layer from the top side. This is top view of the PCB. Oh. Let's do like this. What do you have actually in practice? You will have this tray interconnect, but around it, you will actually pour the copper plane, which is ground on the whole layer. So this will all this will be a ground, but it will have openings where the traces are. So here will be opening, and this part here. So I will just use a color. Part here will be open in terms of ground, but here will be the edge of the ground. So in order to just shield this, we will just put vias. That way, we will confine the field also vertically, I would say. So we will literally have, let's call it like a semi-Faraday cage. Because on the bottom layer, you will also have the ground. And if you look at the cross section, it will look like this. You will have here your tray, and you will have vias around. Basically, it will look like this if you look. On this side and on the, let's say, opposite side, I cannot draw them. So you are just guarding your tray in order not to allow the coupling of the field to surrounding traces, components, and so on. This is how it is done on the PCB. Okay, I hope this was clear. Okay, so let's go back just a second. Okay. Okay, we are here. Okay, so we discussed this clock generated. This is very problematic part. In general, if you can, you would do the following. You would, if you're in the digital domain, you would really always want to put this component. I will just use a laser point. This component as close to this component, and you would like to keep this trace as short as possible. That's the general rule what you would like to do, but obviously, you know, different designs, they dictate different actually conditions. Okay, do you understand this architecture? Do you find it more or less logical, or would you change something here? Sorry? Okay. Okay, so we finally came to the architecture of the system. And in industry environment, it is also like this. It is like iterational process. You have a lot of discussions. You will have a lot of different details in the game, and you need to resolve all that. Once you do that, then we can proceed to something which is called design start. We already tackled that when we were talking about methodological approach, but now we are going to see how that looks like in practice. So let's see. The very first step is component library creation. Before we proceed, how many people worked in Altium or any other tool so far?
Sorry?
So how many people worked in Altium? Okay. Okay. So then I will tackle this in a greater detail here. Okay. So the general approach when you want to start designing something is firstly you need to create so-called component library. What does it mean? It means the following. Just it doesn't work. Yeah, so all these components here, you can see the part numbers. I also put the part numbers here. You literally need to download their data sheets to go to them and then to see the pinout of the component and the footprint. Are you familiar with the footprint? You know what is a footprint of the component? Yes. Okay. So yes. So we firstly create a component library. So as we said, all the selected components need to be drawn in the CAD tool, whatever CAD tool you are using. But this is the procedure you must do. Then, what does that imply? It implies that we need the schematic symbol and we need the footprint. So schematic symbol, that's a symbol, of course, we will use when we should go schematic circuitry. And footprint, of course, that's actually the place on the PCB where your component will be mounted, assembled. And this is actually very critical, because if you make errors at this stage, you can imagine what will happen when you receive your bare PCB and now you want to solder your components there. You just wasted time and you just wasted money. Of course, not in all cases, because sometimes it is possible to do some rework, some patching on a PCB so that you can put the component there. But if we are talking about high-speed components like this oscillator, which is on 100 megs, it's not doable, because you will most probably make a big problem. You will radiate everywhere, and you will most probably create the PCB useless, because you will destroy analog front end, and you will not be able to test at least analog part. Okay, so what do we do there? We do the following. We take data sheets, then we create schematic symbols, as we said. It literally means that we will need to draw this rectangle, then we need to place these pins, all the pins. We will check the pin out or pinning here in the data sheet. And when we enter all this information, then we will proceed for creation of the footprint. So does anyone know how this type of casing of integrated circuit is called?
BGA.
BGA, exactly, BGA. Do you know why BGAs are so handy? I mean, not handy, useful in many sense.
Because they are extremely small.
Okay, that can be a reason. Do you know any other reason?
A lot of connections in a little area.
Yeah, that's also. But there is one specific reason why we want to use BGA.
There isn't wire bonding.
Sorry, there is?
There isn't wire bonding. Ball wire inside the chip.
Because of the wire bonding inside the chip. That's what I heard. Okay. Yeah. That's on the right track. So I will just tackle something very briefly. I will share my whiteboard. This is important. This is important to understand. Okay, so components. Imagine that we have a through-hole resistor. Yeah, so we have these leads very long. And when we put this through-hole resistor in our PCB, we will have some inductance here. Yeah, and it will not be so small in comparison to other components. It will actually be very big, especially for high frequencies and very fast rise and fall edges. And so we have some noise somewhere in the PCB, which is just produced either from power supply, either from oscillator, either from some other components. And if it is coupled here, we'll have some voltage generated. It's a very simple, it's a basic. So one is familiar with this, but this is actually crucial.